Light is the fastest thing in the universe. Nothing outruns it. A single photon crosses from Earth to the Moon in 1.3 seconds, reaches Mars in 3 minutes, and exits our entire solar system in a matter of hours. It seems impossibly fast. But here is the terrifying truth scientists rarely say out loud. Light is slow, agonizingly, hopelessly slow. So slow that even travelling at its absolute maximum, a beam of light launched today toward the nearest star would not arrive for 4 years and 3 months. So slow that an alien civilization with technology 1 million years ahead of ours would still need decades, centuries or millennia to physically reach Earth. The speed of light is not a bridge between worlds. It is a prison wall, and we are all locked inside. If you are ready to see why the universe may have made contact between civilizations nearly impossible, do me a favour and hit that like button and subscribe. It genuinely helps this channel keep making deep dives like this one. Now, let's begin. Light moves at 670 million miles per hour. Nothing in the universe travels faster. Not particles accelerated in the most powerful colliders on Earth. Not the shock waves from collapsing stars. Not the radiation streaming off a supernova at the moment of detonation. Light occupies the absolute ceiling of physical velocity, a speed limit woven into the architecture of space and time by the laws of physics themselves. Einstein proved it in 1905. Every experiment since has confirmed it. The speed of light is not just fast, it is the fastest anything can ever be. And on human scales it feels like magic. Right now, light is completing a task so rapid it makes every other speed in nature seem frozen. A single photon, leaving a flashlight in your hand, reaches the wall across the room in roughly 10 billionths of a second. That same photon, if fired horizontally across the surface of the Earth, would lap the entire planet 7.5 times in a single second. In the time it takes your brain to register the sensation of touching a hot stove, light has already travelled from New York to Los Angeles and back roughly 10 times. The speed is so extreme that for most of human history, scientists genuinely debated whether light moved at all or simply appeared everywhere instantaneously. It was not until 1676 that Danish astronomer Ole Romer calculated a finite speed for light by observing the moons of Jupiter. He noticed that the timing of eclipses shifted depending on whether Earth was moving toward Jupiter or away from it. The difference was caused by light needing extra time to cross the changing distance. His work was groundbreaking, and when Christian Huygens later used Romer's data to calculate a numerical value, the result was roughly 227,000 kilometers per second. Imprecise, but it shattered the idea of instantaneous illumination. Light was fast, unimaginably fast, but it was not infinite. Modern instruments have refined Romer's measurement to extraordinary precision. Light travels at exactly 299,792.458 kilometers per second in a vacuum. Scientists know this number so precisely that they actually use it to define the meter itself. 1 meter is the distance light travels in 1,299,792,458th of a second. The speed of light is not merely measured, it is the ruler against which all other measurements are made. On the scale of everyday experience, this speed is overwhelming. Consider the moon. It hangs in the sky roughly 239,000 miles from Earth. Light crosses that gap in 1.3 seconds. When the Apollo astronauts spoke to mission control from the lunar surface, their words travelled at light speed via radio waves, and the delay was barely noticeable. A conversational pause, a slight hesitation, nothing that would suggest the signal had just crossed 250,000 miles of vacuum. Now extend the beam to the Sun. Our star sits approximately 93 million miles away. Light covers this distance in 8 minutes and 20 seconds. When you step outside and feel the warmth of sunlight on your face, Those photons left the sun's surface before you started brushing your teeth. The sun you see in the sky is not the sun as it exists right now. It is the sun as it existed 8 minutes ago. If the sun vanished this instant, you would continue to see it shining for 8 more minutes before the sky went dark. You would feel its warmth. You would see its light. And all of it would be a ghost. This delay is so short that it barely registers in human consciousness. 8 minutes is trivial. We wait longer for a cup of coffee. But it represents the first whisper of a problem that will grow louder and more terrifying as we push farther into space. Mars, at its closest approach, sits roughly 34 million miles from Earth. Light reaches it in about 3 minutes. At its farthest, when Mars and Earth are on opposite sides of the Sun, the distance swells to 250 million miles and light needs roughly 22 minutes. NASA mission controllers already feel this delay acutely. When the Perseverance rover encounters an obstacle on the Martian surface, the signal reporting the problem takes minutes to reach Earth. The command to stop takes minutes to travel back. By the time instructions arrive, the rover has been driving blind for the better part of half an hour. Even at the speed of light, Mars is far enough away that real-time control becomes impossible. Jupiter lies roughly 484 million miles from the Sun. Light needs about 43 minutes to make the trip. Saturn sits at 886 million miles. Light takes roughly 79 minutes. By the time you reach Neptune, the outermost major planet at approximately 2.8 billion miles, light requires over 4 hours to arrive. The Voyager 1 spacecraft, launched in 1977, is currently the most distant human-made object in space, so far away that a signal from it, travelling at the speed of light, takes approximately 22 hours to reach us. Nearly a full day for a message moving at the fastest speed in the universe. 22 hours. Nearly a full day. And Voyager 1 has not even left the neighbourhood. It has barely crossed the boundary where the sun's influence fades and interstellar space begins. In nearly 5 decades of travel, covering 15 billion miles, Voyager 1 has traversed less than 1/400th of a single light year. This is where the illusion begins to crack. A light year is the distance light travels in 1 year of continuous motion. That's 670 million miles per hour, running non-stop for 365 days. Light covers approximately 5.88 trillion miles. That number is so large that writing it out in standard form requires 13 digits, 5,880 billion miles. And it represents the basic unit of interstellar measurement, the smallest meaningful increment when talking about the distances between stars. The nearest star system to our Sun is Alpha Centauri, a triple star system consisting of Alpha Centauri A, Alpha Centauri B, and their distant companion Proxima Centauri. Proxima Centauri is the closest of the three, sitting approximately 4.24 light-years from Earth. That translates to roughly 25 trillion miles. Let that number settle for a moment. 25 trillion miles. Light, the fastest thing in the universe, needs 4 years and 3 months to cross this gap. A beam of light leaving Earth right now will not reach the nearest star until sometime in 2030, and this is the closest star, the nearest one, the galactic equivalent of the house next door. In 2016, astronomers confirmed the existence of Proxima Centauri b, a roughly Earth-mass planet orbiting within the habitable zone of Proxima Centauri. The discovery electrified the scientific community because it meant there was a potentially rocky world receiving enough energy from its star to possibly support liquid water, right next door in cosmic terms. The planet orbits its red dwarf host once every 11.2 Earth days, sitting far closer to its star than Mercury does to our Sun. Whether Proxima Centauri b actually harbours conditions suitable for life remains deeply uncertain. Its star is a flare star, prone to violent bursts of ultraviolet and X-ray radiation that could strip away any atmosphere. The planet is likely tidally locked, with one face permanently baking and the other frozen in eternal night. As of 2025, We still do not know if it has an atmosphere at all. But the crucial point is not whether Proxima Centauri b is habitable. The crucial point is where it is. 4.24 light-years, 25 trillion miles. Even if it were a perfect twin of Earth, teeming with oceans and oxygen and life, light itself needs more than 4 years to bridge the gap. A radio message sent today would not arrive until 2030. A reply, if anyone were there to send one, would not reach us until 2034 at the earliest. A simple hello and response would consume nearly a decade, and Proxima Centauri is the closest candidate we have. Move outward and the numbers become savage. Barnard's star, the next nearest single star, lies roughly 5.96 light-years away. Recent observations have confirmed planets orbiting it, but none yet confirmed to sit in the habitable zone. Ross 128 sits about 11 light-years away and hosts a planet that may be temperate. Teagardens star, roughly 12.5 light-years distant, hosts Teagardens star b, a world that scored near the top of the Earth Similarity Index when it was discovered in 2019, with a surface temperature estimated near 20 degrees Celsius. That score was later revised downward, but it remains one of the most Earth-like candidates known. Yet light needs 12.5 years to reach it. A radio signal sent in 2026 would arrive in 2038. The TRAPPIST-1 system grabbed global headlines in 2017 when astronomers announced 7 roughly Earth-sized planets orbiting a single ultra-cool red dwarf star, with at least 3 sitting in or near the habitable zone. It was and remains one of the most promising multi-planet systems for studying habitability. But TRAPPIST-1 sits approximately 40 light-years from Earth. Light leaving Earth the year you were born would still not have arrived there if you are under 40 years old. A message sent at the speed of light, the day World War II ended in 1945, would just now be pulling into the system. 40 light-years. That is roughly 235 trillion miles, and in galactic terms, it is still absurdly close. The Milky Way spans at least 100,000 light-years in its visible disk alone. Some recent measurements suggest it may extend to 200,000 light-years or more when you include the outer stellar halo. The galactic center lies approximately 26,000 light-years from Earth. Light that left the center of our galaxy when early humans were painting caves in Europe has still not reached us. It will arrive in roughly 24,000 more years. The galaxy contains an estimated 200 to 400 billion stars. Among those, astronomers now believe that a significant fraction host planets. Statistical analysis of Kepler Space Telescope data suggests there could be billions of Earth-sized planets orbiting in habitable zones throughout the Milky Way. Billions of potential homes for life. Billions of worlds where, in principle, water might pool on rocky surfaces and chemistry might inch toward biology. But those 40 billion worlds are scattered across a disk, 100,000 light-years wide. The average distance between neighboring star systems in our region of the galaxy is roughly 4 to 5 light-years, and in the dense central bulge, stars pack more tightly, perhaps a light-year or 2 apart. In the sparse outer arms where we live, the gaps widen, and the habitable worlds among those stars are not evenly distributed. They are sprinkled randomly across this enormous volume, separated by gulfs measured in light-years, tens of light-years, hundreds of light-years. Here is where the true nature of the speed of light reveals itself. Light is not fast in any meaningful interstellar sense. It is agonizingly, almost comically slow. A photon leaving Earth and heading for the center of the Milky Way will not arrive for 26,000 years. A photon heading for the far side of the galaxy will need 100,000 years. A photon aimed at the Andromeda Galaxy, our nearest major galactic neighbor, will require 2.5 million years to arrive, and these are photons, massless particles, traveling at the absolute maximum speed the universe allows. The speed of light feels fast because humans evolved on a planet 8,000 miles wide, orbiting a star 93 million miles away. On those scales, light is instantaneous for all practical purposes. You flip a switch and the room illuminates. You look at the moon and see it as it was 1.3 seconds ago, a delay no human can perceive. Even the 8-minute delay from the sun is invisible in daily life. But the moment you try to use light speed to connect two star systems, the illusion collapses. The speed that seemed infinite on Earth becomes a crawl between stars. The fastest possible velocity in nature becomes a barrier, not a bridge. It is like discovering that the fastest car ever built can cross a parking lot in a blink, but needs centuries to cross a continent. This mismatch between light's perceived speed and its actual utility over interstellar distances is the central trap of the cosmos. It creates a universe where intelligent civilizations can look up, observe billions of stars, detect the signatures of potentially habitable worlds, and calculate that the galaxy should be teeming with life. But it simultaneously means that reaching those worlds, physically traveling to them, requires confronting a speed limit so restrictive that even the nearest destinations demand timescales measured in decades, centuries, or millennia. And here is the detail that tightens the trap even further. We have been talking about light speed, the theoretical maximum, the absolute ceiling. No material object with mass has ever been accelerated to light speed. No spacecraft, no particle in a collider, no atom in nature reaches that limit. Objects with mass require infinite energy to reach the speed of light. It is not a practical barrier. It is a physical impossibility. The laws of physics encoded in Einstein's special relativity guarantee that any object with mass, no matter how small, can approach the speed of light but never touch it. This means that any physical spacecraft, whether built by humans or by an alien civilization a billion years more advanced, will always travel slower than light. The travel times we have been calculating at light speed are not realistic estimates. They are absolute minimums, theoretical flaws, the fastest possible case. Real travel times will always be longer, usually much longer. Voyager 1, currently humanity's most distant emissary, moves at roughly 17 kilometers per second. That is about 1/17,600th the speed of light. At that velocity, Voyager 1 would need approximately 75,000 years to reach Proxima Centauri. 75,000 years. Human civilization in its entirety, from the first agricultural settlements to the present day, spans roughly 10 to 12,000 years. Voyager 1 would need to fly for 6 times the entire length of recorded human history just to reach the nearest star. Even the fastest spacecraft humanity has ever built, the Parker Solar Probe, skimming the sun at velocities that dwarf anything else in our engineering history, would need thousands of years to cover interstellar distances. These are not theoretical machines from a science fiction novel. These are the real, physical spacecraft we have launched, with the best technology available, and they are comically inadequate for interstellar travel. The gap between what light can do and what our machines can do is not a small engineering shortfall, it is a chasm spanning 4 orders of magnitude. Light is roughly 17,000 times faster than Voyager 1. To close even a fraction of that gap, a spacecraft would need propulsion systems that generate energies far beyond anything humanity has ever produced. This realization changes the way we must think about the Fermi Paradox, the famous question posed by physicist Enrico Fermi in 1950. If the galaxy is so old and so vast and contains so many potential sites for life, where is everybody? The standard answers range from suggesting that intelligent life is exceptionally rare, to proposing that civilizations inevitably destroy themselves, to speculating that aliens are hiding or observing us without contact. But there is a simpler, more physically grounded answer hiding in plain sight. The speed of light itself may be the explanation, not because it prevents civilizations from existing, not because it prevents them from developing advanced technology, but because it prevents them from crossing the distances between stars in any practical time frame. The galaxy may be full of intelligent civilizations, each one looking up at the same sky, detecting the same candidate worlds, dreaming of the same interstellar journeys, and running into the same merciless wall. The speed of light is 300,000 kilometers per second. It sounds fast because it is fast, locally, on tiny scales, in the narrow arena of human experience. But the cosmos does not operate on human scales. It operates on scales where light years are the small unit and galaxies are the medium one. On those scales, the speed of light is not a superpower. It is a leash, a short one. And every calculation we are about to make will show why that leash makes physical interstellar travel not just difficult, but potentially impossible for any civilization that has ever existed or ever will exist in this galaxy. The illusion of speed has one final cruel twist. Because light is also the fastest way to observe the universe, every civilization discovers the cosmos long before it can ever hope to visit it. Telescopes reveal billions of stars. Spectrometers detect the chemical fingerprints of distant atmospheres. Radio dishes listen for signals across the electromagnetic spectrum. An intelligent species can map the galaxy in exquisite detail, catalogue thousands of potentially habitable worlds, and confirm that the raw ingredients for life exist in abundance everywhere it looks. But seeing is not reaching, observing is not arriving. The same speed of light that carries information to our telescopes also sets the upper bound on how fast we could ever physically travel to the sources of that information. The universe lets you look, it lets you wonder, it lets you calculate and dream and plan. And then it tells you the nearest interesting destination is 25 trillion miles away, and nothing you build will ever get there in less than a human lifetime, using any technology that currently exists or is plausibly achievable within the laws of physics. The light that brings us knowledge of the stars is the same light that measures the distance we can never cross. It is simultaneously the messenger and the prison guard, the revealer and the wall. What comes next reveals why even the most ambitious attempts to close this gap run into a barrier that grows worse the harder you push against it. The travel times are only the beginning of the problem. The energy required to achieve those travel times transforms interstellar flight from an engineering challenge into something far more daunting, a confrontation with the fundamental limits of physics itself. Voyager 1 left Earth on September 5, 1977. It carried a golden record etched with sounds and images of human civilization, a message in a bottle tossed into the cosmic ocean. Nearly 5 decades later, it remains the most distant human-made object in existence, sailing through interstellar space at roughly 17 kilometers per second, about 38,000 miles per hour. In everyday terms, that is blisteringly fast. A commercial airplane cruises at 550 miles per hour. A bullet leaves a rifle at roughly 1,700 miles per hour. Voyager 1 travels more than 20 times faster than a bullet every second of every day, without slowing down, without stopping, for almost half a century, and it has covered an almost meaningless fraction of the distance to even the nearest star. In 47 years of continuous flight, Voyager 1 has travelled approximately 15 billion miles. Against the distance we established earlier, Voyager 1 has completed about 0.06% of the journey. If it were pointed directly at Proxima Centauri, which it is not, it would arrive in approximately 75,000 years. That is not a typo. 75,000 years. To put that in context, 75,000 years ago, modern humans had not yet left Africa in significant numbers. The last ice age had not yet reached its peak. Woolly mammoths roamed across Europe and Asia. The entirety of what we call civilization, every empire, every invention, every written word, every war, every symphony, every scientific discovery, fits inside the last 10,000 years. Voyager 1 would need to fly for 7.5 times that span just to reach the nearest star. This is the baseline. This is where humanity currently stands in terms of interstellar capability. Not close, not within reach, not approaching viability. We are so far from interstellar travel at current speeds that the timescales involved exceed meaningful comprehension. Voyager 1 will be a frozen, silent relic drifting through black emptiness for millennia, after human civilization has either transformed beyond recognition or cease to exist entirely. But what if we could go faster? What if we could build spacecraft that dramatically exceed Voyager's velocity? How much faster would we need to go before interstellar travel becomes even remotely plausible? Let us begin climbing the speed ladder and see what happens. At 1% of the speed of light, a spacecraft would travel at approximately 3,000 kilometers per second, or about 6.7 million miles per hour. This is roughly 176 times faster than Voyager 1. It is a speed so extreme that no human-built object has come anywhere close to achieving it. The Parker Solar Probe, the fastest spacecraft ever flown relative to the Sun, peaked at roughly 190 kilometers per second during its closest solar passes. 1% of light speed is nearly 16 times faster than that. At this velocity, a journey to Proxima Centauri would take approximately 425 years. That is shorter than Voyager's 75,000-year estimate by a factor of almost 200. It sounds like progress. But 425 years is still an enormous span of time. When Columbus crossed the Atlantic in 1492, the journey took about 2 months. A 425-year mission to Proxima Centauri would mean that if a ship had launched during Columbus's era, it would still not have arrived. The crew who launched the mission would have been dead for centuries. Their grandchildren would have been dead for centuries. The civilization that built the ship might not even exist anymore by the time it reached its destination. Reaching Teegarden's star at 1% of light speed would take roughly 1,250 years. The TRAPPIST-1 system, at 40 light-years, would require 4,000 years. 4 millennia. That is older than the Egyptian pyramids. A spacecraft launched at 1% of the speed of light toward TRAPPIST-1 at the dawn of ancient Egypt would still be in transit today, with another 2,000 years of travel remaining. 1% of light speed is not nearly fast enough. Push to 5%. At 5% of light speed, roughly 15,000 kilometers per second, or about 33.5 million miles per hour, the numbers start to compress. Proxima Centauri drops to roughly 85 years. Teegarden's star falls to about 250 years. TRAPPIST-1 shrinks to 800 years. These are still multi-generational timescales, but for the nearest targets, we are finally approaching something that overlaps with a long human lifespan. An astronaut who departed at age 20 might, in theory, arrive at Proxima Centauri at age 105. Unlikely to survive the trip, but at least the journey fits within the outer boundary of biological possibility. The problem is that 5% of light speed represents an almost incomprehensible engineering leap. No propulsion system ever built or seriously tested comes close. Chemical rockets, the technology that powers every spacecraft humanity has ever launched, top out at exhaust velocities of roughly 4 to 5 kilometers per second. Ion engines, like those used on the Dawn spacecraft, achieve higher exhaust velocities but produce minuscule thrust, suitable for slow spirals through the inner solar system, not for interstellar sprints. Nuclear thermal propulsion, studied extensively during the NERVA program in the 1960s, offers roughly double the efficiency of chemical rockets. Still, nowhere near enough. Even fusion-powered spacecraft, which remain entirely theoretical, would struggle to reach 5% of light speed. The most optimistic designs from the Project Daedalus study conducted by the British Interplanetary Society in the 1970s envisioned a massive unmanned probe weighing 54,000 tons at launch, using inertial confinement fusion to accelerate to about 12% of light speed. But Daedalus was never more than a theoretical exercise. No fusion engine capable of sustained thrust has ever been built, and the fuel requirements were staggering. The probe would have needed 50,000 tons of deuterium and helium-3, a fuel that exists in such small quantities on Earth that harvesting sufficient amounts would likely require mining the atmosphere of Jupiter. Push to 10% of light speed. Now the numbers become more tempting for the nearest targets. Proxima Centauri at 10% light speed takes roughly 42 years. A mission launched when an astronaut is 25 years old arrives when they are 67. Difficult. brutal on the human body after decades in microgravity and confined spaces. But within a single human lifetime, this is the threshold that many researchers identify as the minimum viable speed for a crewed interstellar mission to the nearest star. But look beyond Proxima Centauri and the trap reasserts itself. Teagardens star, at 10% light speed, takes 125 years, 2 full human lifetimes. TRAPPIST-1 takes 400 years. Any star beyond about 15 light-years requires multi-generational timescales, even at 10% of light speed. And 10% of light speed is 30,000 kilometers per second, a velocity so extreme that the engineering challenges are nearly as daunting as the distances themselves. What about 20%? The Breakthrough Starshot project, announced in 2016 with $100 million in funding from physicist and investor Yuri Milner and supported by Stephen Hawking and Mark Zuckerberg, aimed to accelerate a spacecraft to 20% of the speed of light. At that velocity, Proxima Centauri would be reachable in roughly 21 years. A message sent back at light speed would arrive at Earth about 4 years later. Total mission time from launch to data return, approximately 25 years. This is genuinely within a single human career. A scientist who helps launch the mission in their 30s could analyze the results in their 50s. But the Breakthrough Starshot design was not a crewed vessel. It was not even a traditional probe. It was a gram-scale chip, a spacecraft weighing about 1 gram, roughly the mass of a paperclip, attached to a meter-scale reflective sail. The plan called for an array of ground-based lasers with a combined output of 100 gigawatts to fire at the sail for roughly 10 minutes, accelerating the chip to 20% of light speed through sheer radiation pressure. The spacecraft would carry a tiny camera, basic sensors, and a minimal communication system. It would fly through the Alpha Centauri system in a matter of hours, snap a few images, and attempt to transmit them back to Earth using an onboard laser powered by the energy it could collect. Even this minimal concept proved overwhelmingly difficult. By September 2025, Scientific American reported that the Breakthrough Starshot project had been placed on indefinite hold. Of the $100 million pledged, only about $4.5 million had actually been spent across roughly 30 contracts. The engineering challenges were simply too severe. The laser array required gigawatt-scale power that no existing facility could provide. The sail material needed to be almost perfectly reflective, because absorbing even a tiny fraction of 100 gigawatts of laser energy would vaporize it instantly. The chip needed to survive acceleration forces of thousands of G and then endure 40 years of interstellar space, including bombardment by dust grains that at 20% of light speed would impact with the energy of small explosions. Communication back to Earth from 4 light-years away using a chip-sized transmitter presented unsolved problems in signal power and beam coherence. And this was for a paperclip mass flyby probe, not a crewed ship, not a landing mission, not even a probe that could slow down an orbit. A 1-gram chip screaming through the Alpha Centauri system at 60,000 kilometers per second, getting a few hours of observation before vanishing into the interstellar void forever. If 20% of light speed is this difficult for 1 gram of payload, the implications for anything heavier are devastating. Consider what a meaningful interstellar mission would actually require. Not a chip, a spacecraft capable of supporting scientific instruments, communication equipment, a power source, shielding against interstellar dust and cosmic radiation, and potentially a deceleration system. Even a modest unmanned probe designed to enter orbit around a target star would need to mass hundreds or thousands of kilograms. A crewed vessel capable of supporting human life for decades would mass tens of thousands of tons at minimum, accounting for life support, food, water recycling, radiation shielding, medical facilities, and the psychological requirements of keeping a crew functional during a journey lasting longer than most careers. The relationship between payload mass and the difficulty of reaching interstellar speeds is not something that scales kindly. There is a reason that no realistic interstellar mission profile ever proposes sending a crewed vessel at anything close to the speed of light. And that reason comes down to a fundamental equation in rocketry that we will confront directly very soon. For now, it is enough to understand the core principle. The fuel needed to accelerate a heavier spacecraft itself adds mass, which requires more fuel, which adds more mass. The faster you want to go, the more fuel you need, and the more fuel you carry, the heavier you become, which demands yet more fuel. This cascading penalty turns interstellar speeds into a problem that does not merely grow with ambition, it explodes. This is why no realistic interstellar mission profile ever proposes sending a crewed vessel at anything close to the speed of light. The energy and fuel costs do not scale kindly, they scale mercilessly. But the travel time problem has another dimension beyond raw speed, one that is easy to overlook but equally devastating: biological lifespan. Every organism we know of has a finite life. Humans, even under the best medical conditions available today, rarely survive past 110 or 120 years. The average lifespan in developed nations hovers around 80 years. A mission to Proxima Centauri at 10% of light speed takes about 42 years, survivable in principle for a young, healthy crew. A mission to a star 20 light-years away at the same speed takes 200 years. No human alive today, and no human who will be born under currently understood biology, can live that long. This biological clock applies not only to humans but almost certainly to any biological organism that might evolve elsewhere in the galaxy. While we cannot know the lifespans of alien species, the fundamental constraints of biology suggest that all carbon-based life faces thermodynamic limits on longevity. Cells accumulate damage, DNA degrades. Metabolic processes generate waste products that eventually overwhelm repair mechanisms. Even if an alien species lives 5 times longer than humans, say 500 years, a mission lasting 1,000 years at 5% of light speed to a star 100 light-years away still exceeds their biological window. The standard response to the biological lifespan problem is to propose generation ships, vessels large enough to sustain a self-reproducing population across many generations. The crew that launches the mission is not the crew that arrives. Their descendants, born and raised entirely aboard the ship, complete the journey. This concept has been explored extensively in science fiction and has received some serious academic analysis. The challenges are monumental. A generation ship would need to be a fully self-sustaining ecosystem, recycling all air, water, and nutrients indefinitely. It would need to support a population large enough to maintain genetic diversity across centuries, which geneticists estimate at a minimum of several hundred to several thousand individuals. It would need energy sources capable of running for millennia without resupply. It would need social structures robust enough to maintain mission coherence across dozens of generations, preventing internal conflict, cultural drift, or the simple loss of institutional knowledge about why the mission exists and where it is going. No human organization has ever maintained a coherent institutional mission for more than a few centuries. Religions and some governmental structures come closest, but even those undergo radical transformation over spans of 500 or 1,000 years. The idea that a ship-based civilization could maintain a coherent objective across 30 or 50 generations, with each new generation choosing to continue a journey they never chose to begin, requires a level of social engineering that has no historical precedent. Suspended animation offers a theoretical alternative. If crew members could be placed into a state of metabolic suspension, their biological clocks effectively paused, they could survive journeys lasting centuries. Science fiction routinely depicts this technology as cryogenic freezing, where passengers are cooled to near absolute zero and revived upon arrival. In reality, no technology capable of reversibly freezing and reviving a complex multicellular organism exists, and the obstacles are formidable. Water expands when it freezes, rupturing cell membranes. Ice crystals shred delicate tissue structures. Even vitrification, a rapid cooling technique that avoids ice crystal formation, has been demonstrated only in very small tissue samples and individual organs under laboratory conditions. Whole-body suspended animation for humans remains firmly in the realm of speculation. But even if a spacecraft could somehow carry its crew across decades or centuries, whether through biological endurance, generation ships, or suspended animation, it still must survive the journey itself. And interstellar space, far from being a passive vacuum, is an actively hostile environment that degrades everything passing through it. The space between stars is not truly empty. It contains the interstellar medium, a thin haze of hydrogen atoms, helium, trace heavier elements, and dust grains. The average density is roughly 1 atom per cubic centimetre, a vacuum far more extreme than anything achievable in a laboratory on Earth. But at relativistic speeds, even this whisper of matter becomes lethal. A spacecraft travelling at 10% of the speed of light moves at 30,000 kilometers per second. At that velocity, every hydrogen atom in the interstellar medium impacts the spacecraft's forward surface with the kinetic energy of a high-energy particle. The cumulative effect is equivalent to standing in front of an intense beam of radiation. Engineers working on the Breakthrough Starshot concept calculated that at 20% of light speed, the interstellar medium would deliver a radiation dose to the spacecraft's leading surface comparable to the inside of a particle accelerator. Over years and decades of transit, this bombardment would degrade electronic components, erode structural materials, and slowly destroy any unshielded surface. Dust grains present an even more dramatic hazard. The interstellar medium contains microscopic solid particles, silicates, carbon compounds, ice crystals, typically measuring fractions of a micrometer across. On Earth, these would be invisible to the naked eye. But kinetic energy scales with the square of velocity. A dust grain massing 1 nanogram, a billionth of a gram, striking a spacecraft at 10% of light speed carries kinetic energy equivalent to roughly 450 joules. That is comparable to the muzzle energy of a small handgun round. A single invisible speck of interstellar dust would punch through the hull of any conventional spacecraft like a bullet through paper. At 20% of light speed, the energy quadruples. Each dust grain impact becomes equivalent to a rifle round. Over a journey lasting decades, a spacecraft would encounter millions of such particles. The cumulative damage would be catastrophic without shielding far more massive than anything currently achievable, and every kilogram of shielding added to the spacecraft increases the total mass, which increases the fuel requirement, which compounds the rocket equation penalty we have already discussed. Cosmic rays add another layer of degradation. These high-energy particles, primarily protons accelerated to near light speed by supernova shockwaves and other astrophysical processes, permeate the galaxy. On Earth, our atmosphere and magnetic field shield us from the worst of them. In interstellar space, there is no such protection. Cosmic rays penetrate spacecraft hulls, ionize atoms in electronic circuits, corrupt data stored in computer memory, and damage biological tissue. Over the course of a multi-decade mission, the cumulative radiation dose from cosmic rays alone poses severe risks to both living crew and electronic systems. NASA has studied the effects of cosmic radiation extensively in the context of Mars missions, which would expose astronauts to elevated radiation for roughly 2 to 3 years. The findings are sobering. Extended exposure increases cancer risk, damages the central nervous system, and may accelerate cognitive decline. Studies on rodents exposed to simulated cosmic ray environments showed measurable brain inflammation and impaired memory. An interstellar mission lasting 40 or 80 or 400 years would subject its crew or its electronic systems to radiation doses orders of magnitude higher than a Mars mission. Without shielding far beyond current capability, the crew would face cumulative biological damage that no medical intervention could reverse. And then there is the slow, relentless decay of the spacecraft itself. Every mechanical system degrades over time. Seals crack, lubricants evaporate, metal fatigues. Electronic components drift out of specification. On Earth, we maintain complex machines through constant repair and replacement of parts. The International Space Station, the most complex structure ever built in space, requires continuous resupply from Earth and constant maintenance by its crew. It has been operational for roughly 25 years and already shows significant wear. An interstellar spacecraft would need to operate for decades or centuries with no resupply, no replacement parts from external sources, and no possibility of rescue if something fails. Every component must either last for the full mission duration or be repairable using only materials and tools carried on board. This demands engineering margins and redundancy levels that no human project has ever achieved. The longest operating spacecraft in history, the Voyager probes, have survived roughly 5 decades, and both are experiencing progressive instrument failures as their radioisotope thermoelectric generators decay and their electronics age, extending that operational lifespan to centuries or millennia under the additional stresses of relativistic dust bombardment and cosmic radiation represents a challenge without precedent. These environmental hazards do not merely add inconvenience to the travel time problem, they compound it fundamentally. Long travel times are not just boring or logistically difficult, they are actively destructive. The longer the journey, the more damage the spacecraft accumulates, the more likely a critical system fails, and the lower the probability that anything functional arrives at the destination. The interstellar medium is not a passive stage on which the drama of travel plays out. It is an adversary, eroding the mission with every passing year. There is also the problem of what happens to the civilization that launches the mission. Suppose an alien species sends a generation ship toward a star 100 light-years away at 5% of light speed. The journey takes 2,000 years. During those 2,000 years, the home civilization continues to exist, to develop, to advance. Technologies improve. New propulsion methods may be discovered. Faster ships may be built. It is entirely possible, perhaps even likely, that a ship launched centuries after the original would overtake the generation ship and arrive first. The original crew or their descendants would arrive to find the destination already colonized by their own civilization's later efforts. This is sometimes called the weight calculation or the incessant obsolescence problem. It suggests that launching an interstellar mission before propulsion technology is sufficiently mature is not just wasteful, but actively counterproductive. You are better off waiting until you can go fast enough that no future ship will beat you there. But this creates an infinite regress. There is always a reason to wait for better technology. The mission never launches. The combination of extreme travel times, biological mortality, generation ship complexity, interstellar environmental hazards, and the obsolescence problem creates a devastating trap for any civilization contemplating interstellar travel. Even if you can build a ship that reaches 10% of light speed, the number of accessible targets within a single biological lifetime is vanishingly small, perhaps a handful of star systems within 20 or 30 light-years. Beyond that radius, every mission becomes multi-generational, demanding social, engineering, and survivability solutions that may be fundamentally unachievable. And the galaxy is not 30 light-years across. It is 100,000 light-years across at minimum. The vast majority of stars, the vast majority of potentially habitable planets, the vast majority of wherever alien civilizations might exist, sit at distances that require travel times spanning thousands, tens of thousands, or hundreds of thousands of years, even at ambitious fractions of light speed. Let us make this concrete with a specific example. Suppose an alien civilization exists around a sun-like star in the Sagittarius arm of the Milky Way, roughly 30,000 light-years from Earth. They are technologically advanced. They have mastered fusion propulsion and can accelerate a large spacecraft to 5% of the speed of light, a capability far beyond anything humans currently possess. They aim their ship at Earth. At 5% of light speed, the journey takes 600,000 years. 600,000 years ago on Earth, Homo sapiens did not yet exist. Neanderthals were still hundreds of thousands of years in the future. The dominant hominids were Homo heidelbergensis, a species most people have never heard of. The continents were in approximately the same positions they occupy today, but the climate was radically different, oscillating between glacial and interglacial periods. The entire arc of human evolution, from the emergence of our species in Africa to the construction of particle accelerators and space telescopes, fits comfortably inside the travel time of this hypothetical mission. If that alien civilization launched their ships 600,000 years ago, it would be arriving right about now. But what are the odds that a civilization maintains the institutional will, the technological infrastructure, and the physical resources to support a 600,000-year mission? What are the odds that the ship itself survives 600 millennia of interstellar space, enduring micrometeorite impacts, cosmic ray degradation, mechanical wear, and the slow decay of every material component? Even if we grant generous assumptions about alien engineering, the timescales are crushing. A civilization capable of building a ship that lasts 600,000 years would need to be stable across a span of time that dwarfs the entire history of complex life on Earth's land surfaces. That is not an engineering problem. That is a question about the fundamental nature of civilizational persistence. Whether any organized society, biological or otherwise, can maintain coherence across geological time. Push the numbers further. A civilization on the far side of the galaxy, 90,000 light-years away, attempting to reach Earth at 5% of light speed, faces a journey of 1.8 million years. At 10% of light speed, 900,000 years, even at the wildly optimistic speed of 50% of light speed, a velocity that would require energy expenditures beyond any plausible projection, the trip takes 180,000 years. The Milky Way is roughly 13 billion years old. It has had plenty of time for civilizations to arise, develop, and attempt expansion. But the speed of light ensures that crossing the galaxy is not a matter of centuries or even millennia. It is a matter of hundreds of thousands to millions of years. Each journey is a civilizational marathon with no guarantee that the runners will still be alive or still be civilizations when they reach the finish line. This is the travel time trap. It is not a single barrier but a series of compounding constraints. Distances are enormous. Achievable speeds are a tiny fraction of light speed. Travel times exceed biological lifespans for all but the nearest targets. Generation ships face engineering and social challenges with no proven solutions. The interstellar environment actively degrades every spacecraft that enters it. The obsolescence problem discourages launching missions at suboptimal speeds, and the galaxy is so vast that even relativistic travel times stretch across geological epochs. The trap applies equally to any civilization, regardless of how advanced it is. An alien species with 1 million years of technological development still faces the same speed limit. They still cannot exceed the speed of light. They may build faster ships than we can imagine, but those ships will still travel at some fraction of light speed, and the distances remain unchanged. No amount of technological progress can shrink the galaxy. No amount of engineering brilliance can make Proxima Centauri closer than 4.24 light-years, or make the galactic center closer than 26,000 light-years. The speed of light does not discriminate between primitive and advanced civilizations. It constrains all of them equally. And for the vast majority of star systems in the Milky Way, the travel times it imposes are so extreme that physical contact between civilizations becomes not merely difficult, but functionally impossible within any reasonable definition of a mission, a lifespan, or a civilization's continuity. But the travel time trap is only half the story. We have been calculating how long interstellar journeys take. We have not yet asked the question that makes the problem exponentially worse. How much energy does it cost to reach those speeds? The answer is where interstellar travel transitions from merely impractical to something approaching physical impossibility. The energy wall ahead is higher than most people can imagine, and what sits behind it is even worse. Every spacecraft ever launched by human civilization has been powered by controlled chemical explosions. Liquid hydrogen and liquid oxygen combine in a combustion chamber, producing superheated steam that blasts out of a nozzle at roughly 4.5 kilometers per second. The rocket moves forward. Newton's third law in action. This is the technology that carried the Apollo astronauts to the moon, that lofted the Hubble Space Telescope into orbit, that delivered rovers to the surface of Mars. It works brilliantly for reaching Earth orbit and navigating the inner solar system. It is laughably inadequate for interstellar travel. The reason comes down to a single concept that governs all of rocketry: exhaust velocity. A rocket moves forward by throwing mass out the back. The faster that mass is ejected, the more efficiently the rocket converts fuel into speed. Chemical rockets eject exhaust at roughly 4 to 5 kilometers per second. To reach a final velocity significantly higher than your exhaust velocity, you need exponentially more fuel. This relationship is captured in the Tsiolkovsky rocket equation, derived by Russian scientist Konstantin Tsiolkovsky in 1897, and it is the single most important equation in spacecraft design. The equation is deceptively simple. The final velocity of a rocket depends on the exhaust velocity multiplied by the natural logarithm of the ratio between the rocket's initial mass and its final mass. What this means in practice is devastating. If your exhaust velocity is 5 kilometers per second and you want to reach 50 kilometers per second, you need a mass ratio of roughly 22,000 to 1. For every kilogram of payload you want to deliver at that speed, you need 22,000 kilograms of fuel at launch, and 50 kilometers per second is pathetically slow by interstellar standards. It is less than 0.02% of the speed of light. At that velocity, reaching Proxima Centauri would take approximately 25,000 years. To reach even 1% of the speed of light, 3,000 kilometers per second, with a chemical rocket, the mass ratio becomes a number so large it has no physical meaning. You would need more fuel than exists in the observable universe to accelerate a single kilogram to 1% of light speed using chemical propulsion. This is not an exaggeration. It is arithmetic. The exponential nature of the rocket equation makes chemical rockets fundamentally incapable of interstellar travel at any meaningful speed. This is why every serious proposal for interstellar propulsion abandons chemical energy entirely and looks to nuclear physics. Nuclear reactions release roughly 1,000,000 times more energy per kilogram of fuel than chemical reactions. A kilogram of uranium undergoing fission produces about 80 trillion joules of energy. A kilogram of hydrogen-oxygen propellant produces about 13 million joules. The difference is a factor of approximately 6 million. Nuclear energy offers a path to exhaust velocities that are orders of magnitude higher than chemical rockets, which dramatically improves the mass ratios required for high-speed travel. But even nuclear energy has limits, and those limits become visible disturbingly quickly when you start calculating the requirements for interstellar speeds. Consider the energy needed to accelerate a modest spacecraft to 10% of the speed of light. Let us define modest conservatively. Not a crewed vessel, not a generation ship. A robotic probe massing 1,000 kilograms, roughly the weight of a small car. This is far heavier than the Breakthrough Starshot concept, but far lighter than anything capable of carrying humans or sophisticated scientific instruments. The kinetic energy of a 1,000 kilogram object moving at 10% of the speed of light is calculated using the relativistic kinetic energy formula. At 10% of light speed, relativistic effects are still small, so the classical approximation works reasonably well. 1/2 times mass times velocity squared. The velocity is 30 million meters per second. Squaring that gives 9 times 10 to the 14th. Multiply by 500, half the mass in kilograms, and you get 4.5 times 10 to the 17th joules. 4.5 times 10 to the 17th joules. That is 450 quadrillion joules. To put this in perspective, the total energy consumption of the entire United States in a year is approximately 1 times 10 to the 20th joules. The energy needed to accelerate a single small probe to 10% of light speed is roughly 1/200th of America's annual energy consumption. For one probe, weighing 1,000 kilograms, going only 10% of light speed. Scale up to a more meaningful spacecraft. A crewed vessel capable of supporting even a small crew for a multi-decade journey would need to mass at least 100,000 kilograms, and that is an extremely optimistic estimate that ignores radiation shielding, redundant life support, and the structural mass needed to contain a pressurized habitat. At 100,000 kilograms, the energy requirement jumps to 4.5 times 10 to the 19th joules. That exceeds the annual energy output of most nations. Now push the speed higher. At 20% of light speed, the kinetic energy quadruples compared to 10%, because energy scales with the square of velocity. At 50% of light speed, the energy is 25 times higher than at 10%, and relativistic corrections begin adding significant additional cost. At 90% of light speed, the relativistic mass increase means the actual energy needed is many times higher than the classical formula would suggest. The total energy required to accelerate a 100,000 kilogram vessel to 90% of light speed exceeds 10 to the 22nd joules. That is roughly 20 times the total annual energy consumption of human civilization, concentrated into the propulsion of a single ship. These numbers are not theoretical curiosities. They represent hard physical constraints. Energy cannot be created from nothing. It must come from somewhere. Fuel must be carried, generated, or collected. And the more energy you need, the more fuel you must carry, which adds mass, which increases the energy requirement, which demands more fuel. The rocket equation's exponential penalty applies at every stage. This is why propulsion researchers focus so intensely on exhaust velocity. The higher the exhaust velocity, the less fuel you need for a given final speed. Fusion rockets, if they could ever be built, would achieve exhaust velocities in the range of 10,000 to 30,000 kilometers per second, roughly 3 to 10% of light speed. This dramatically reduces the mass ratios compared to fission or chemical rockets. A fusion-powered spacecraft reaching 10% of light speed might need a mass ratio of only 10 or 20 to 1, challenging but conceivable in principle. But no fusion engine capable of sustained, controlled thrust has ever been built. The entire field of fusion energy, despite 7 decades of research and tens of billions of dollars in investment, has not yet produced a commercially viable power plant on Earth, let alone a propulsion system capable of operating in space. The ITER experimental fusion reactor in France, the most ambitious fusion project in history, is designed to demonstrate net energy gain from fusion, but will not achieve full deuterium-tritium fusion operations until the late 2030s at the earliest, after decades of delays and cost overruns. It is a stationary building-sized facility. Converting fusion into a compact, reliable spacecraft engine that can operate continuously for years or decades represents an additional engineering leap of enormous proportions. Antimatter propulsion represents the theoretical upper limit of energy density. When a particle of matter meets its antiparticle, they annihilate each other completely, converting 100% of their combined mass into energy. This is vastly more efficient than any other known energy source. Fission converts roughly 0.1% of mass into energy. Fusion converts roughly 0.7%. Antimatter annihilation converts 100%. A single kilogram of antimatter annihilating with a kilogram of normal matter would release approximately 1.8 times 10 to the 17th joules, enough to accelerate a small probe to a meaningful fraction of light speed. The problem is producing antimatter. Current particle accelerators can create antimatter in vanishingly small quantities. The total amount of antimatter ever produced by all of humanity's particle accelerators combined is estimated at roughly 20 nanograms. Not 20 grams. 20 nanograms. 20 billionths of a gram. Producing even 1 gram of antimatter using current technology would cost on the order of tens of trillions of dollars and take millions of years of continuous accelerator operation. Producing the kilograms or tons needed for a starship is so far beyond current capability that it borders on the meaningless to discuss as a near-term option. But there is a deeper problem with antimatter that is rarely discussed and frequently misunderstood. Antimatter is not a source of energy. It is a storage medium, and it is a catastrophically inefficient one. Creating antimatter requires energy input. In particle accelerators, high-energy collisions produce particle-antiparticle pairs from the kinetic energy of the colliding particles. The process obeys conservation of energy with absolute strictness. To create a positron, you must invest at least the energy equivalent of the positron's rest mass, plus the rest mass of the electron created alongside it, plus whatever kinetic energy the collision products carry away. In practice, the efficiency of current accelerators at producing antimatter is measured in billionths of a percent. For every billion joules of energy pumped into the accelerator, only a few joules worth of antimatter comes out. The rest is lost as heat, radiation, and kinetic energy of particles that do not produce useful antiparticles. Even a theoretically perfect process cannot beat break-even. The absolute minimum energy required to create an antiparticle is equal to the energy that antiparticle will release upon annihilation. You cannot get more energy out of antimatter than you put into making it. At best, you get the same amount back. In reality, you always get less, because no conversion process is perfectly efficient. Antimatter does not generate energy. It merely stores it in an extraordinarily compact form and returns a fraction of the original investment upon annihilation. This means that a civilization fueling an interstellar mission with antimatter must first generate all of the required energy through some other means, whether fusion, fission, stellar collection, or something else entirely. Then it must pay the enormous efficiency penalty of converting that energy into antimatter. Then it must store the antimatter without losses for the duration of the mission preparation and the journey itself, a period potentially spanning decades. The total energy infrastructure required to produce mission-ready quantities of antimatter would dwarf the energy content of the antimatter itself, potentially by orders of magnitude. Antimatter does not solve the energy problem of interstellar travel. It relocates the problem, wrapping it in an additional layer of inefficiency that makes the total energy budget even more punishing than the raw kinetic energy calculations suggest. Storage presents equally formidable challenges. Antimatter annihilates on contact with any normal matter. It must be contained in a perfect vacuum using magnetic or electric fields, a technology called a penning trap. Current traps can hold tiny numbers of antiparticles for limited durations. Scaling this to contain macroscopic quantities of antimatter, keeping it perfectly isolated from the walls of its container and from stray gas molecules for the duration of a multi-decade mission, would require engineering breakthroughs that do not currently exist even in theoretical form. Laser sail propulsion, the approach chosen by Breakthrough Starshot, sidesteps the fuel problem by leaving the energy source behind. Instead of carrying fuel, the spacecraft is pushed by a beam of light fired from a stationary installation. The spacecraft carries no propellant at all. Its mass can be minimized. The energy comes from a ground-based or space-based laser array, which can draw power from conventional sources. This approach has genuine theoretical advantages. It eliminates the tyranny of the rocket equation because the spacecraft does not need to carry its own fuel. The laser array can be scaled up over time, reused for multiple launches and powered by renewable energy. This is why Breakthrough Starshot chose it as the most plausible path to relativistic speeds. But laser sails face their own devastating constraints. The laser array must deliver enormous power over enormous distances. Breakthrough Starshot envisioned a 100 gigawatt laser array, roughly equivalent to the total electrical generating capacity of a medium-sized country, focused on a sail only meters across. The beam must remain tightly focused across millions of kilometers as the spacecraft accelerates away from Earth. Diffraction, the natural spreading of light beams over distance, means that the array must be kilometers in scale to maintain a sufficiently tight beam, and the acceleration phase lasts only minutes. Once the spacecraft outpaces the beam's ability to push it, it coasts freely for the remaining decades of the journey. Most critically, laser sails can only push. They cannot pull. The beam accelerates the spacecraft away from the laser source, but it provides no mechanism for slowing down at the destination. A laser sail spacecraft arriving at Proxima Centauri at 20% of light speed would scream through the entire star system in a matter of hours and continue into interstellar space forever. It would be a flyby mission, not an arrival, not an orbit insertion, not a landing. A brief glimpse, then permanent departure. This brings us to the cruelest dimension of the energy problem: deceleration. Every discussion of interstellar travel speeds focuses on acceleration. How fast can we get going? But arriving at a destination requires stopping, or at least slowing down enough to enter orbit or conduct extended observations. And slowing down costs just as much energy as speeding up. If you accelerate a spacecraft to 10% of light speed, you must spend a certain amount of energy to reach that velocity. If you then want to decelerate to rest at the destination star, you must spend the same amount of energy again, applied in the opposite direction. The total energy budget for a mission that both arrives at speed and stops at its target is not double the acceleration energy. It is worse, because the fuel needed for deceleration must itself be accelerated during the first half of the trip, adding to the initial mass and compounding the rocket equation penalty. For a conventional rocket, the deceleration problem is devastating. A ship that needs a mass ratio of 20:1 for acceleration alone needs a mass ratio of approximately 400:1 for acceleration plus deceleration, because the mass ratio compounds multiplicatively. You are not just carrying fuel for the outbound trip, you are carrying fuel for the braking phase, plus the fuel needed to accelerate that braking fuel to cruise speed, plus the fuel needed to accelerate the fuel that accelerates the braking fuel. The exponential penalty applies twice, and the result is mass ratios so extreme that the mission becomes physically impossible for any payload larger than trivial. This is why the only interstellar mission concepts that use onboard propulsion for both acceleration and deceleration tend to be enormous. Project Daedalus, the British Interplanetary Society's 1970s design study, proposed a two-stage fusion-powered probe that would accelerate to 12% of light speed, but not decelerate. It was a flyby mission by design, because the mass penalty for deceleration was unacceptable. A follow-up study called Project Icarus attempted to address deceleration but found that the mass requirements roughly quadrupled, pushing the design to the edge of feasibility even on paper. Some researchers have proposed alternative deceleration methods that do not require onboard fuel. A magnetic sail, for example, could theoretically interact with the charged particles of the interstellar medium, creating drag that gradually slows the spacecraft. The interstellar medium contains roughly 1 hydrogen atom per cubic centimetre. At high speeds, these atoms impact the magnetic sail and transfer momentum, producing a braking force. But the interstellar medium is extraordinarily sparse. The braking force from a magnetic sail is tiny. Decelerating from 10% of light speed using a magnetic sail would take decades or centuries, depending on the sail's size and the medium's density. And the deceleration phase would begin long before the destination star, meaning the spacecraft would need to deploy the sail millions or billions of kilometers in advance and crawl the final stretch at progressively slower speeds. Another concept uses the destination star's own light as a braking mechanism. A solar sail deployed near the target star could reflect stellar photons, creating a force that opposes the spacecraft's motion. This is elegant in principle, but requires the spacecraft to approach the star at a trajectory and speed that allows the stellar radiation pressure to make a meaningful contribution. At 10% of light speed, the kinetic energy of the spacecraft is so enormous that stellar radiation pressure would need an impractically long time to bleed off that velocity. The spacecraft would either overshoot the system before slowing sufficiently, or need to begin braking maneuvers at extreme distances from the star. The deceleration problem applies to any civilization, not just ours. An alien species sending a spacecraft to Earth faces identical physics. They must either carry enough energy to decelerate, doubling or quadrupling their mission's energy budget, or accept a flyby mission that offers only hours of observation during the brief passage through our solar system. If they choose deceleration, the energy costs become so extreme that the mission transitions from merely staggering to nearly impossible. If they choose a flyby, the scientific return is minimal. A few snapshots of a planetary system taken at 30,000 kilometers per second, with no ability to orbit, land, or make prolonged observations. There is a tempting counterargument at this point. Surely a sufficiently advanced civilization could solve these problems. Perhaps they have discovered energy sources we cannot imagine. Perhaps they have physics we have not yet uncovered. Perhaps their engineering capabilities are so far beyond ours that the constraints we face are trivial to them. This argument misunderstands the nature of the constraints. The speed of light is not an engineering limitation. It is a law of physics. It is embedded in the structure of space-time itself. It is not analogous to the sound barrier, which was once thought to be an absolute limit but was broken by faster aircraft. The sound barrier is a feature of air. The light speed barrier is a feature of the universe. It does not depend on what you are made of, how smart you are, or how advanced your technology is. It applies to all matter and energy equally, everywhere, always. Similarly, the rocket equation is not an engineering limitation. It is a consequence of conservation of momentum, one of the most fundamental and rigorously tested laws in all of physics. No amount of technological advancement can change the fact that accelerating mass requires expelling other mass, and the energy needed to do so scales with the square of the velocity and compounds exponentially with the mass ratio. Better engines can improve exhaust velocity, which helps. But even a perfect engine, one that converts mass into directed energy with 100% efficiency, still faces the relativistic energy requirement. The energy needed to approach the speed of light grows without bound as you approach it. This is not a wall that can be broken with a bigger hammer. It is the shape of space-time. An alien civilization 1,000,000 years older than humanity would certainly possess capabilities we cannot foresee, but they would still be operating within the same physical universe. Their ships would still have mass. Their fuel would still carry energy. Their journeys would still be governed by relativity. They might build fusion engines where we cannot. They might produce antimatter in quantities we consider impossible. They might construct laser arrays spanning entire solar systems. All of these would be extraordinary achievements, and all of them would still leave the civilization constrained to speeds below light, facing energy costs that scale brutally with velocity, and dealing with a deceleration problem that doubles the already enormous bill. The most generous possible scenario for an advanced civilization's interstellar capability might look something like this. They master antimatter production and storage, creating fuel with 100% mass energy conversion. They build a spacecraft that carries enough antimatter to accelerate to 50% of the speed of light and then decelerate to rest at the destination. The mass ratio for such a mission, even with a perfect engine, would be roughly 3:1. For every kilogram of payload, they need 3 kilograms of total propellant, half of which must be antimatter. For a meaningful mission carrying 1,000,000 kilograms of payload, they need roughly 1,000,000 kilograms of antimatter. Producing that much antimatter would require energy inputs of at least 9 times 10 to the 22nd joules at perfect theoretical efficiency, and real production efficiency would multiply that figure by many orders of magnitude. This is not impossible for a sufficiently advanced civilization. A Type 2 civilization on the Kardashev scale, one capable of harnessing the entire energy output of its host star, could in principle generate such energies. But it would represent a colossal investment for a single mission, and even at 50% of light speed, the trip to a star 50 light-years away takes 100 years. A trip to a star 500 light-years away takes 1,000 years. A trip across the galaxy takes 200,000 years. The energy wall does not prevent interstellar travel entirely, but it ensures that every mission is extraordinarily expensive. Every journey to anywhere beyond the nearest stars takes lifetimes or longer, and every civilization must weigh the crushing cost against the uncertain return. The physics does not care how advanced you are. A kilogram of matter travelling at half the speed of light carries a fixed amount of kinetic energy. That energy must come from somewhere. It must be generated, stored, and directed. The laws of thermodynamics impose efficiency limits on every energy conversion process. The rocket equation imposes mass penalties on every propulsion system. And the deceleration problem doubles the bill for any mission that wants to do more than take photographs while screaming past at relativistic speed. These constraints do not mean that no civilization in the galaxy has ever attempted interstellar travel. They mean that any civilization that has attempted it has done so against the full weight of physics, at enormous cost, across daunting timescales, and with severe limits on how far and how fast they can go. The speed of light does not merely slow interstellar travel down, it makes every mission a calculation of diminishing returns, where the costs escalate exponentially and the distances stretch beyond any plausible mission duration. The energy wall is real, the deceleration trap is real, and together with the travel time problem we already confronted, they form a three-sided prison that confines every civilization, no matter how brilliant, to its own small corner of the galaxy. What comes next will explore the final dimension of this prison, the one that forces us to confront the possibility that the universe was never designed to be crossed, and that the silence of the cosmos is not a mystery but a consequence. The Milky Way galaxy is at least 13 billion years old. It began forming within a few 100 million years of the Big Bang, assembling itself from collapsing clouds of hydrogen and helium, igniting its first generation of stars, and building spiral arms that would eventually stretch across 100,000 light-years of space. For most of that 13 billion year history, the galaxy has contained billions of stars, trillions of planets, and conditions broadly compatible with the chemistry of life. Earth is 4.5 billion years old. Life appeared here within the first billion years, possibly within the first few 100 million. If our planet is any guide, biology does not wait long to establish itself once conditions allow. The raw ingredients, liquid water, organic molecules, energy gradients, existed on Earth almost as soon as the surface cooled enough to support them, and those same ingredients exist throughout the galaxy. Water is one of the most common molecules in the universe. Carbon chemistry is ubiquitous. Energy sources, from stellar radiation to geothermal heat to radioactive decay, are available on virtually every rocky world. As of early 2026, astronomers have confirmed more than 6,000 exoplanets, with thousands more candidates awaiting verification. The Kepler Space Telescope's statistical analysis suggested that roughly 20% of Sun-like stars host an Earth-sized planet in their habitable zone. Applied across the galaxy's estimated 200 to 400 billion stars, this yields a figure of approximately 40 billion potentially habitable worlds orbiting Sun-like stars alone. Add red dwarf stars, which are far more numerous and also host rocky planets in their habitable zones, and the number climbs higher still. The galaxy has had billions of years and billions of potential venues. If life arises with any reasonable probability on suitable worlds, the Milky Way should contain not just life, but ancient life. Civilizations that emerged billions of years before Earth even formed. Species that have had millions or tens of millions of years to develop technology, expand their capabilities, and contemplate the stars. This is the foundation of the Fermi Paradox. In 1950, over lunch at Los Alamos National Laboratory, physicist Enrico Fermi reportedly looked up at his colleagues and asked a question that has haunted science ever since. Where is everybody? If the galaxy is old enough and large enough and rich enough in habitable worlds for intelligent life to have arisen many times over, why do we see no evidence of it? No signals, no probes, no megastructures, no visitors. The sky is silent. The solar system is empty. As far as every instrument we possess can determine, we are alone. Dozens of explanations have been proposed over the 7 decades since Fermi's question. Perhaps intelligent life is far rarer than the numbers suggest. Perhaps civilizations inevitably destroy themselves through nuclear war, environmental collapse, or artificial intelligence gone wrong. Perhaps they exist but choose not to communicate, hiding deliberately in a dark forest where announcing your presence invites destruction. Perhaps they are so alien that we cannot recognize their signals. Perhaps we are being observed and simply do not know it. Each of these explanations addresses the paradox from a different angle, but there is one explanation that is so physically grounded, so rigorously supported by the laws of nature, that it deserves to stand apart from the speculation. It is the explanation we have been building from the very beginning. They cannot get here, not because they do not exist, not because they do not want to, not because they lack the intelligence or the technology, but because the speed of light, the absolute maximum velocity in the universe, is too slow to make physical interstellar travel practical across the distances that separate most star systems. The energy costs are too high, the travel times are too long, the deceleration problem is too severe, and the galaxy is far, far too large. This is not a failure of alien ambition, it is a feature of the universe itself. Before going further, it is essential to draw a sharp distinction that is often blurred in popular discussions. There are three fundamentally different things an alien civilization could attempt across interstellar distances, and the difficulty varies enormously among them. The first is observing Earth. This is the easiest. Light from our planet radiates outward in all directions at the speed of light. Any civilization with sufficiently advanced telescopes could, in principle, detect Earth's presence, analyze our atmosphere's chemical composition, and determine that our world harbors conditions consistent with life. This requires no travel. It requires only patience and good instruments. A civilization 50 light-years away observing Earth today would see our planet as it existed 50 years ago, and they could do this without leaving their home star system. The second is sending signals to Earth. This is harder but still achievable in principle. Electromagnetic signals, whether radio waves, laser pulses, or any other form of light, travel at the speed of light. A civilization could broadcast a message toward Earth, and it would arrive after a delay equal to the distance in light years. A signal from Proxima Centauri takes 4 years. A signal from the center of the galaxy takes 26,000 years. Communication is possible but slow, agonizingly slow for distant civilizations. A simple exchange of messages with a civilization 1,000 light-years away would take 2,000 years minimum. Entire empires rise and fall in less time. The third is physically reaching Earth, sending matter, whether a probe, a ship, or living beings, across interstellar space. This is the subject of this entire journey, and it is incomparably harder than either observation or signaling. Physical travel requires not just crossing the distance, but carrying mass across it, accelerating that mass to a significant fraction of light speed, shielding it from the interstellar environment for decades or centuries, and potentially decelerating it at the destination. The energy costs, as we have already seen, are staggering. The time costs are crushing, and no shortcut around the speed of light has ever been demonstrated. The failure to distinguish between these three activities leads to persistent confusion in public discussions of alien contact. People often reason that because the galaxy is old and large, aliens must have had enough time to reach us, but this conflates signaling distance with travel distance. A civilization might easily observe Earth from 1,000 light-years away. Sending a signal to Earth from that distance is straightforward, if slow, but physically traveling to Earth from 1,000 light-years away, at 10% of light speed, takes 10,000 years and requires energy expenditures that would strain a stellar-scale civilization. The Fermi Paradox is specifically a paradox about physical presence. We see no alien ships, no alien probes, no alien artifacts in our solar system. The question is not why they have not called, but why they have not come. And the answer, grounded in everything we have examined, is that coming here is almost inconceivably difficult. Let us revisit the numbers one final time, now with the full weight of everything we have established. The nearest star system is 4.24 light-years away. Even at 10% of the speed of light, a velocity that demands energy equivalent to a significant fraction of a nation's annual output, for even a modest probe, the journey takes over 40 years one way. At 5%, it takes 85 years. At 1%, 425 years. These are the travel times to the closest possible destination. Now consider a civilization located not next door, but at a more typical galactic distance. The average separation between stars in our region of the galaxy is 4 to 5 light-years, but habitable worlds are not evenly distributed. A civilization looking for a specific type of target, say an Earth-like planet orbiting a Sun-like star with confirmed biosignatures, might need to search across hundreds or thousands of light-years before finding one. If the target is 500 light-years away, and the spacecraft travels at 10% of light speed, the journey takes 5,000 years. At 5%, 10,000 years. At 1%, 50,000 years. These timescales exceed any known or plausible biological lifespan. They exceed any known organizational continuity for a civilization. They exceed most estimates for the lifespan of technological societies, which some researchers place at a few hundred to a few thousand years based on extrapolation from human history. A mission lasting 10,000 years requires not just a spacecraft that functions for 10 millennia, but a civilization that remains committed to receiving its data for 10 millennia. That civilization must maintain the technological infrastructure to detect the spacecraft's transmissions, the institutional memory to understand what the mission was, and the cultural continuity to care about the results. No human institution has lasted 10,000 years. The oldest continuously operating organizations on Earth, certain religious institutions and governmental structures, span roughly 1 to 2,000 years and have undergone radical transformation during that time. The idea that a civilization could launch a mission and maintain readiness for its return signal across 10,000 years assumes a level of stability that has no precedent in the only example of civilization we know. But perhaps aliens are not biological. Perhaps they have transcended biology entirely, uploading their consciousness into machines, becoming artificial intelligences capable of operating across arbitrary timescales. This is a common suggestion in discussions of the Fermi Paradox, and it deserves careful consideration. An artificial intelligence does not age. It does not need food, water, or oxygen. It does not suffer from boredom, loneliness, or psychological breakdown during a 10,000-year journey. In principle, an AI-controlled probe could be launched toward a distant star and function perfectly for millennia, requiring only a power source and radiation-hardened computing hardware. This is the concept behind von Neumann probes, self-replicating machines that could theoretically spread across the galaxy without any ongoing support from their home civilization. The idea, first proposed by mathematician John von Neumann, envisions a probe that arrives at a star system, uses local resources to build copies of itself, and launches those copies toward additional star systems. Each copy does the same. The process repeats exponentially, and within a few million years the probes could theoretically visit every star in the galaxy. The mathematics of von Neumann probes suggest that even at modest speeds, 1 or 2% of light speed, self-replicating probes could colonize the entire Milky Way in roughly 10 to 100 million years. That sounds like a long time, but it is less than 1% of the galaxy's age. If any civilization anywhere in the galaxy had launched von Neumann probes at any point in the last several billion years, the probes should have reached every star system by now, including ours. They have not. Or if they have, we see no evidence of their presence. This absence is sometimes cited as evidence against the existence of advanced civilizations, but the von Neumann argument contains assumptions that may not survive scrutiny. It assumes that self-replicating machines can be built reliably, that they can function across millions of years without accumulating fatal errors, that they can extract and process resources in arbitrary star systems, and that no failure mode, whether mechanical, computational, or environmental, halts the replication chain before it spans the galaxy. Each of these assumptions is enormous. Self-replicating machines of the complexity required for interstellar travel and resource extraction have never been built. The closest analogy in nature is biological life itself, and biological replication is famously error-prone, requiring elaborate error correction mechanisms that still fail over long timescales, producing mutations, cancers, and extinction. A machine replicating across millions of years and millions of star systems would face analogous degradation. Cosmic rays would flip bits in computer memory. Micrometeorite impacts would damage structural components. The resources available in each star system would vary unpredictably, requiring the probe to adapt its manufacturing processes, a capability that implies a level of artificial general intelligence we have not achieved. Even granting that these challenges could be solved, the speed of light still constrains the expansion rate. Von Neumann probes traveling at 1% of light speed cover 1 light-year per century. Spanning the galaxy's 100,000 light-year diameter would take 10 million years. At 5%, 2 million years. These are short compared to the galaxy's age, which is why the Fermi Paradox retains its force. But they assume no failures, no delays, no dead ends. In practice, the expansion would be slower, patchier, and more fragile than the idealized exponential model suggests. And critically, even if von Neumann probes could eventually reach every star system, they solve only the problem of presence, not the problem of contact. A self-replicating probe arriving in our solar system would be a machine, not a civilization. It would carry information from its creators, but those creators might be dead, evolved beyond recognition, or located tens of thousands of light-years away. Communication with the probe's home civilization would face the same light-speed delays that plague every other form of interstellar interaction. Sending a message and receiving a reply could take centuries or millennia. By the time the home civilization learns that their probe found something interesting in our solar system, the probe may have been here for thousands of years. Von Neumann probes do not solve the Fermi Paradox. They reframe it. The question shifts from, why have aliens not visited, to, why do we see no evidence of self-replicating machines? And the most physically grounded answer may simply be that building and sustaining such machines across galactic timescales is far harder than the elegant mathematics of exponential replication suggests. What about wormholes? General relativity permits solutions to Einstein's field equations that describe tunnels through space-time, shortcuts connecting distant points without traversing the intervening space. If a civilization could create or find a stable wormhole, it could theoretically step from one star system to another instantaneously, bypassing the speed of light entirely. The problems with wormholes are severe. Every known solution that describes a traversable wormhole requires exotic matter, a hypothetical substance with negative energy density. No exotic matter has ever been observed or produced. Its existence is not forbidden by known physics, but neither is it supported by any experimental evidence. The energy requirements for creating or stabilizing a wormhole large enough to pass a spacecraft through are estimated at levels comparable to the total mass energy of a planet or a star. And even the theoretical models that permit wormholes suggest they would be extraordinarily unstable, collapsing the instant anything attempted to pass through unless sustained by continuous input of exotic matter. The Alcubierre warp drive, proposed by Mexican physicist Miguel Alcubierre in 1994, describes a different mechanism. Instead of tunneling through space-time, the warp drive contracts space in front of the spacecraft and expands it behind, creating a bubble that effectively moves faster than light, while the spacecraft inside remains stationary relative to its local space. This does not violate special relativity because the spacecraft itself never exceeds light speed locally. Only the surrounding space moves. The original Alcubierre model required negative energy densities comparable to the mass energy of the observable universe, making it physically absurd. Subsequent refinements have reduced the energy estimates dramatically, but they still require exotic matter in quantities that have never been produced or observed. A 2021 paper by physicist Eric Lentz proposed a warp drive solution that uses only positive energy, but the energy requirements remained astronomical, and the concept has not been experimentally validated. As of 2026, Warp drives remain theoretical constructs with no experimental support, no confirmed mechanism for producing the required space-time distortions, and no pathway from concept to engineering. It is critical to be honest about what these speculative concepts represent. They are mathematical possibilities within the framework of general relativity. They are not technologies. They are not engineering proposals. They are solutions to equations that describe the geometry of space-time, and they require conditions that have never been observed anywhere in the universe. A civilization that could manufacture exotic matter in planetary quantities, stabilize wormholes, or generate controlled space-time distortions would be operating at energy scales so far beyond anything we can extrapolate that invoking them to solve the Fermi Paradox is essentially equivalent to invoking magic. This is not a dismissal of future physics. It is possible, perhaps even likely, that the universe contains phenomena and principles we have not yet discovered. But responsible reasoning about the Fermi Paradox requires working within the physics we know, not the physics we wish for. And the physics we know says that the speed of light is an absolute limit, that the energy costs of approaching it are enormous, and that no known mechanism allows circumventing it. This brings us to a subtler but equally important point. The phrase sufficiently advanced civilization is often invoked as though technological advancement eventually transcends the laws of physics. It does not. A civilization 1,000,000 years old will certainly possess capabilities we cannot predict, but those capabilities will still operate within the framework of physical law. They will not violate conservation of energy. They will not violate conservation of momentum. They will not break the speed of light in vacuum. Technological progress does not change the constants of nature. It learns to work within them more efficiently. Humanity went from horse-drawn carts to jet aircraft in roughly 2 centuries, an increase in travel speed of about 3 orders of magnitude. But we did not change the laws of aerodynamics or thermodynamics to do it. We found more efficient ways to exploit those laws. The same principle applies at cosmic scales. A civilization far older than ours might build fusion engines, produce antimatter, construct planet-sized laser arrays, and engineer materials of extraordinary resilience. These would be astonishing achievements, but each one operates within the known laws of physics, and none of them circumvents the speed of light. The critical distinction is between engineering barriers and physical barriers. An engineering barrier is something that is difficult, but not forbidden by physics. Building a fusion reactor is an engineering barrier. It is staggeringly hard, but nothing in the laws of nature prevents it. A physical barrier is something that the laws of nature prohibit regardless of engineering capability. Traveling faster than light in vacuum is a physical barrier. It is not a matter of building a better engine. It is a fundamental property of space-time. Conflating these two categories leads to the false intuition that a civilization advanced enough could do anything, including break the speed of light. It cannot. The universe does not negotiate. Time dilation offers one final partial consolation, and it deserves honest examination. Einstein's special relativity predicts that time passes more slowly for objects moving at high velocities relative to a stationary observer. A spacecraft travelling at 90% of the speed of light would experience time dilation such that for every year that passes on the ship, roughly 2.3 years pass on Earth. At 99% of light speed, the factor increases to about 7. At 99.9%, it reaches roughly 22. In principle, this means that a crew travelling at very high relativistic speeds could cross vast distances while aging only modestly. A ship travelling at 99% of light speed could reach a star 100 light-years away in approximately 101 years of Earth time, but the crew would experience only about 14 years of subjective time. The galaxy's 100,000 light-year diameter could be crossed in roughly 14,000 years of ship time at that speed, compared to 100,000 years of Earth time. This sounds transformative, and it is, for the travellers, but it does nothing for the civilization that launched them. The homeworld still ages at the normal rate. If you send a crew to a star 100 light-years away, At 99% of light speed, 101 years pass at home before the ship arrives. A round trip would take over 200 years of Earth time. The crew would return to a civilization that had advanced by 2 centuries, where everyone they knew had been dead for generations. They would be temporal refugees, stranded in their own future. Moreover, reaching 99% of the speed of light requires an enormous amount of energy, far beyond anything produced on a planetary scale. The relativistic kinetic energy of a spacecraft at 99% of light speed is roughly 6.1 times its rest mass energy. For a 100,000 kilogram vessel, that is approximately 5.5 times 10 to the 22nd joules. That is roughly equivalent to the total energy consumption of human civilization over an entire century, concentrated into the propulsion of a single ship. No known or projected technology can deliver such energies. Antimatter annihilation with perfect efficiency would require roughly 300,000 kilograms of antimatter, a quantity that exceeds total human antimatter production by a factor beyond meaningful comprehension. Fusion would require even more fuel due to lower conversion efficiency. And the deceleration problem doubles everything. Time dilation is real physics. It is confirmed by experiments with particle accelerators and precise atomic clocks on aircraft and satellites. But exploiting it for practical interstellar travel requires speeds so extreme that the energy costs become physically prohibitive for any conceivable civilization. It is a theoretical escape hatch with a lock that no one has the key to. When you assemble all of these constraints, acceleration energy, deceleration energy, mass ratios, biological lifespan, civilizational continuity, interstellar environmental hazards, the absence of exotic matter, the failure of every proposed shortcut to survive contact with experimental reality, and the inescapable distinction between engineering barriers and physical barriers, a picture emerges that is both simple and profound. The speed of light is not a bridge between civilizations. It is a wall. It permits observation. It permits communication, albeit with delays measured in years, decades, or centuries. But it effectively prohibits physical travel between all but the very nearest star systems. And even those nearest journeys require energy expenditures and mission durations that place them at the extreme edge of what any civilization could plausibly achieve. The galaxy is not empty. It may be teeming with life. Billions of worlds orbiting billions of stars, chemistry becoming biology, biology becoming intelligence, intelligence becoming technology. Civilizations rising, flourishing, and gazing up at the same sky we gaze upon, detecting the same exoplanets, running the same calculations, reaching the same devastating conclusion. The distances are too great, the speeds are too slow, the energy costs are too high, and the universe does not offer a shortcut. This is the cosmic prison. Not a prison of bars and walls, but a prison of geometry and velocity. The galaxy is structured so that intelligent life can arise in abundance but cannot easily make contact. Each civilization occupies its own island, surrounded by an ocean of space-time that light itself needs thousands of years to cross. They can see the other islands in the distance. They can detect the smoke from other fires, but they cannot build a boat fast enough to reach them. The terrifying truth embedded in everything we have explored is not that aliens do not exist. It is almost certainly the opposite. In a galaxy this old, this vast, and this rich in the ingredients of life, the probability that we are alone approaches zero. Something is out there. Many somethings, perhaps. Thinking, building, wondering, searching. But the universe may be structured so that they can never reach us, and we can never reach them. The speed of light, which we once celebrated as the fastest thing in existence, is in fact the mechanism of our isolation. It is the cosmic speed limit that ensures every civilization remains trapped in its own neighborhood, separated from every other civilization by gaps that no ship can practically cross, no signal can quickly bridge, and no technology yet imagined can eliminate. The silence of the sky is not evidence of absence. It is evidence of distance. The Fermi Paradox may not be a paradox at all. It may simply be the natural consequence of a universe where the speed of light is fast enough to illuminate the cosmos but too slow to connect it. We are not alone, but we may be permanently alone in every way that matters, surrounded by life we can never meet, neighbours we can never visit, minds we can never know. Each of us, every civilization that has ever looked up at the stars, sits inside its own quiet pocket of the dark, able to see the light from distant fires but unable to cross the space between them before the fire goes out. The speed of light is not our highway to the stars. It is the silence between them. And in that silence, every civilization that has ever existed may have asked the same question we are asking now, staring into the same vast, beautiful, unreachable sky. Where is everybody? They are right there, impossibly far away, impossibly out of reach, burning their own brief fires on their own small worlds, separated from us not by malice or indifference, but by the simple, merciless geometry of a universe that lets you look but never lets you touch. The speed of light is the loneliest number in physics, and it always will be.